Thank you. Especially, I would like to thank Zheming and Yongchen for inviting me to here. I'm really happy that I see you again, or old friend or new friend, because last year at that time, probably I'm in a very dangerous situation. So I think probably I'd never see you again. But fortunately, I'm here, so I'm so happy. And today I would like to talk about a very, very new work that just done by my student and I. The student, Mr. Yang, actually is the first year of the graduate school. So he's a very bright young man, young student. And I changed the title a little bit, specify what means causality break. So I specify it in the internal causality break and entanglement emergence in quantum loop. Okay, so what we are looking for is actually ask a fairly basic questions that probably everybody asked. Why entanglement emerges only in quantum region, not in the classical world? This is looks like a fairly simple question, but actually it's not that clear, at least to me, okay? So let's go back to a little bit about a brief review about the quantum entanglement. As everybody knows that entanglement is introduced in the EPR papers in 1935. It questioned a kind of instance correlation in the distance systems that there's not any interaction between them, or any kind of interaction can be ignored, based on the probability interpretations that Einstein and Prof and Rosen asked. So it was later called as a spoken distance in action by Einstein. And then after 30 years, the problem seems to be solved because Bayer developed inequality. Inequality is based on the probability was introduced some kind of local variables. And then the correlation between non-interacting distance system must obey inequality. And Bayer also shows that such kind of inequality is violated by the entanglement state. And then after 80s of the last centuries, many experiments verified such kind of properties, especially the Klaus Aspen and Seligman won the Nobel Prize in Physics in 2022. So it seems everything is clear, at least so far. The entanglement is a real quantum phenomenon. But the question I'd like to ask is, do we really understand the quantum entanglement fully, clearly? Well, let's ask a few questions, whether or not we can answer them. The first question I just asked, actually it is the main topic that we are focused on in the paper. Why entanglement emerges in quantum region, but not in the classical world? Well, some people may argue that Bayer inequality answers this question, but actually not. Bayer inequality never touched anything about the quantum dynamics and also nothing to do with the classical dynamics. It's only used the probability theory to calculate the correlation with the local variables. So Bayer inequality only excludes the possibility to have the local hidden variables for probability interpretation, but it does not answer the above questions. And more deeply, people may ask, what is the physical origin of entanglement? Or more deeply, what is the probability interpretation? Because everything comes from the probability interpretation, as stated in the EPR papers, right? So those are questions that essentially rise from the EPR paradox, but up to now, still not have answers. So let's go back to a little bit about what the entanglement talk about in the EPR papers. That's called the sort experiment. Well, you consider two particles stay in a wave function, put over there. It is the stimulus eigenstate of x1 minus x2 and p1 plus p2, the position and the momentum operators. And then if you do the measurement on the momentum of the particle 1, you will immediately, the wave function collapse to the state that space also gave you the particular momentum of the particle 2. That's the instant interaction that violated our common sense. Okay. If you measure the momentum, you get the same things. So then people questioned about the reality and the locality of the wave functions. But before people ask such questions, maybe you should think about the wave function that EPR presented here is a real physical meaningful, or it is actually has a problem. In fact, a plane wave is well defined in the classical physics, but it's not a physical acceptable wave function in quantum mechanics, because plane wave has a probability, equal probability in the whole space. The whole space is infinitely large, so you cannot get the probability interpretations. So it already has a problem over there. And about the non-locality, let's go back. What kind of intelligence that we can create in experiment? Actually, all kind of entanglement, as we already heard in the morning's talk, all kind of entanglement actually is created by the local theory. For example, from the first fundamental theory developed by the Diracs about the QED, relativistic quantum mechanics, then by the covalent QED, and then go to the non-abelian gauge theory, so that you get the weak interaction or strong interaction. All those interactions actually are local, precisely local theory. So all the phenomena so far we can observe in the nature is originally generated by the local theory, not the non-local. The fundamental interaction is local. Without interaction, it's harder to get entanglement. So today, actually, I want to put a new example that we don't have such kind of interaction to generate the entanglement. And then, what kind of proposals that we can make to see how the entanglement is emerging, and what kind of physical laws that break in the classical mechanics that we usually take over. Okay, so here is some specific quantities that I should emphasize. All the entanglement is generated from the local theory. The non-locality of entanglement is only a phenomenon, not the fundamental essentials. Okay, so what we need to understand is the physical origin of the entanglement. Rely deeply on the probability interpretation of quantum mechanics, as was originally shown in the original EPR papers. And of course, probability interpretation has perfectly explained almost all kinds of experiments that so far associated with the quantum systems. So, what is the question we really have in mind? Here is actually the basic question that was pointed out by Steven Weinberger in the 2016 lectures. His talk is about what's the matter with quantum mechanics. Actually, that's the key point that he pointed out. The Schrödinger equations plus Born's probability interpretation is the fairly well and counterintuitive theory, such a kind of combination. And even up to today, this is still a problem. Nobody can really understand it, right? So quantum mechanics is an counterintuitive theory. Then we should believe that the debugger study from the burn of the quantum mechanics is still continuous and has not been solved yet today. So Bayes inequality only provide the counter-proof method to test the non-locative quantum mechanics. Experiment by Clauser, Aspect, and others once again verified that quantum mechanics is correct. And the Solig's experiment just pioneered the quantum information science, a new research field. But what Einstein really questioned in his paper is about the origin of the probability interpretation wave function and the physical mechanism about the wave function collapse. And those problems still not